All right, so we're going to talk about something called a direction field. So let's say we have a derivative of a differential function and that it gives the slope of tangent lines at the points of its graph. So because y is some function of y, we define it to be a first-order differential. It's necessarily a differentiable function on its interval of definition. Also must be continuous. The corresponding solution curve on the interval must have no breaks and must possess a tangent line at each point. The function f in the normal form is called the slope function or rate function. Okay, now, suppose the corresponding solution x comma y represents any point in the region of the xy plane over the function is defined. The value of f of xy for that function, f assigns to a point, represents the slope of a line, or as we envision it, a line segment called a lineal element. So I feel like I kind of jumped in here and started reading definitions to you. So what we're going to do is we're going to say, all right, so let's say we don't have a solution to a differential equation. What can we do with it then? And the answer is, well, we can actually do a lot. So we're going to take a look at, and again, we don't know how to solve differential equations yet. So right now all of this is new to us, but we can still identify and interpret certain elements of information from the differential. So that's what we're looking at. And we're saying that this derivative of dy dx, from Cal 1, represents slope. So we're essentially looking at a series of small, tiny slopes around that. So let's kind of go through the process here and look at a specific example. And when we look at a specific example, that's where that lineal element comes in. When we collect up several of these things, we actually break up something called a slope field or direction field, which we'll get to in a second. Okay, so how does this whole lineal element work? So we take our function. So our differential equation of dy dx equals 0.2xy, and we're going to sort of create a function at a specified point here. Now we're just going to look at a point. So let's look at f of, say, 2 comma 3. Right, f of 2 comma 3 would be 0.2 times 2 times 3. And if we type that in a calculator, we get something like 1.2. Okay, so what does that physically mean? That means when I'm graphing the point 2 comma 3, so right there, there is a slope through that point that has a slope of 1.2. So think of it like up 1.2 over 1. So not quite a 1-to-1 ratio, but maybe a little bit steeper at that particular point. So that's a single point in that field. And what happens if we look at a collection of those points? So let's kind of get to that element in the lesson. Okay, so if we systematically evaluate f over a set of points, and draw a line element for each point, we create this sort of graphic that represents a series of slopes. So this collection of line elements we refer to as a direction field or a slope field. Try to write that a little bit neater for you. So direction field or a slope field. And then a single solution curve that passes through a direction field must follow the flow pattern, again, based on some initial conditions. So let's take a look at this example here. Now, I'm going to speed this process up with some technology, and I'll show you kind of the website you can use to do this. It's not unusual for very simplistic slope fields to be done by hand, but the more complicated slope fields typically will be done through a calculator, or through paper and pencil. So just kind of like I did with that one element where I looked at one single point. But for the most part, we typically will encourage students to use technology for something like that. So let me pull up this website and I'll walk you through that. All right, so we're going to go to Google. and we're just going to type Desmos, and I'm going to do slope field. And that should pull up this link, and I will put this link in the lesson here so you can kind of see an illustration of this particular slope field, which is 2x over y. Let's look at that one example that we had with sine. So let's see. So I'm just going to come in here and delete this out. And I want sine of x plus y. Okay, so that's an image of it. Now, the way this particular grid is formed, we can't really, like, zooming in and zooming out doesn't really give us too much more detail other than allows us to zoom in around. And you'll see this black dot here. Now, this black dot is a lineal measure, so it's a lineal point that allows us to take an ordered pair, and it plugs it into the formula and gives us a what's happening for the slope at that point. Now, the whole point about the solution curve bit is if I know an initial value, so say I know this initial value, I can kind of follow this along, and you kind of want to think of it like a video game where you're, that's flat, so I go this way, and it's curving down, it's sort of forcing me to go this way, and so that looks like it's asymptotic at that point. Or maybe I start here, and this point, if I keep following the slope, it's going to alter on me and curve that way, and eventually it's going to hit that asymptote at some point. So anyway, so that's a quick version of a slope field for the one that we were looking at. So let's do the slope field for the first example that we looked at, so that 0.2xy, and see what that looks like. All right, so come back in here, 0.2 x comma y. So look like that, and I think we can even find our 2-3 point. Let's see. So over 2, up 3. So, and that kind of matches what we had done by hand. But you can kind of see if we graph a lot of those, that's what that image kind of looks like. So if I wanted to include a particular solution, again, you have to give me an initial value, some sort of ordered pair that it goes through, and then I just kind of follow the curve and trace out what would happen at a particular path. So it looks like if an initial point in this top one, if I get anything above the x-axis, it's going to look like some sort of quadratic of some flavor. And then down here, if I get an initial value that happens to be below the x-axis, I'm going to get sort of a reflection of that. Alright, so an ordinary differential equation in which the independent variable does not appear explicitly is said to be autonomous. So A-U-T-O-N-O-M-O-U-S. I don't know if me spelling it helped or not, but there you go. So an autonomous. If the symbol x denotes an independent variable, then an autonomous first-order differential equation can be written as f of y comma y prime equals 0, or in normal form. Again, normal form is where we just have dy dx on the left and then some function on the right. So, kind of two quick illustrations. Let's say I have dy dx equals 1 plus y squared. That would be autonomous because there is no variable x in that expression. It's all measured in terms of y. Or a non-autonomous is that one we did earlier with the 0.2xy. In that case, the slope is defined by a relationship between x and y itself. Symbols other than x and y are routinely used to represent dependent and independent variables. For example, if t represents time, then inspection of the following. And we saw this when we looked at application problems.